So we saw two things. One was the normal distribution, right? We saw basically two plots so far. One is that I told you people there is this normal distribution, the inverted bell curve, and then a drop like this. Okay, so the definition, the example of heights of people in a town, and this happens to be the degree distribution of nodes in a real world network. We see this. Okay. Now, before asking why do we see a very different kind of a plot here, while in most of the situations we see this kind of a plot, before asking this question, we would like to ask individually why and how does this come about. This one. Same time, why and how of this as well. So to begin with, let me ask the why and how of this normal distribution. How does normal distribution come by? Okay, let us take a look at a nice example and try to motivate the reason behind why the normal distribution appears in nature. Okay, here is an example. I invite you all to think a little about it. Okay, it's not very difficult to understand. It's pretty straightforward. Okay, so assume I pick a random number randomly. I pick randomly a number from 1 to 100. One of these numbers I pick some one number. Okay, and then you as another person, you also pick randomly some number from the same set, 1 to 100. Some number you will pick randomly here. Alright, good. Now, see, when I pick a number randomly here from 1 to 100, I can pick any number. It could be a 1, it could be a 2, it could be a 3, it could be a 50, 60, 70, 73, 89, 100, whatever I want. When you pick as well, you will have the liberty to pick any number you want. Let's assume 10 such people pick. Okay, I am the first person, you are the second person, so on and so forth. Some 10 people pick like this. Okay, 10th person also picks a number from 1 to 100. Okay, right? So what I'm now going to do is, let's say the number here that I pick, let me call it R1. The number you picked, I call it R2. The third person picks a number, I'm going to call it R3, and so on. And the 10th person who picks the number, that number is R10. Okay, so let me go to the next slide. Let me write down. There are 10 random numbers, each one between 1 to 100. Each of these random numbers are from 1 to 100. Here is an important question. While each of these random numbers can be anything from 1 to 100, just in case I added them, look at this, just in case I added all these, what will this be? See, each one of these can be a number from 1 to 100, which means the sum will be at the least it will be 1 plus 1 plus 1 10 times. Assume all of them chose 1 1 1 each, then at least it will be 10, and a maximum of how much? If each one of them picked 100, it will be 100 100 100 10 times, it will be 1000. So this is the least and this is the maximum, the minimum and the maximum. Okay, but then But then observe here that any number 10, 11, 12 up to 1000 can appear for what? For the sum. Correct? But here's the climax. While whatever numbers you pick can be any number between 1 to 100, when you take these 10 numbers and add them, what you get as an answer is not uniformly at random from these numbers, which means 10 and 11 do not appear uniformly at random here. While let's say in R10, 1 and 2 and 3 and whatnot up to 100 appears randomly. Each one of them has the same chance of appearing here. But then the chances of 10 appearing here is less than the chances of 11 appearing here. Is less than the chances of, let's say, 12 appearing here in this place. And why is that? If you can think, you will come to a conclusion that this is indeed once again a bell curve. Right? It's going to be, if I were to plot the values, let's say the least was what? 11, 12, so on up to, it will go on and on up to, let's say 1000 is the maximum. You will observe that uniform. Let me go back to the previous slide. So each one of them, each one of R1 can be on an average, let's say anything from 1 to 100, so on and so forth. So this will be roughly, so this will be like this. The plot will look like this. Right? It's good to write a program and then check. Let me assign that to you. Assignment for you all is to write a piece of Python code, to check this. You'll be surprised to see that it is actually a very beautiful curve like this. Okay, to check this. Right? So why does this happen? That's very obvious. It's very unlikely that you pick a 1 and a 1 and a 1 for all of them. Correct? It is equally unlikely that you pick a 100 and a 100 and a 100 for all of them. Correct? So what is more probable as a sum is, if you have guessed it right, it is roughly around 500. Actually 550, but roughly around 500 plus. Right? That will be the most free. That's the peak here, rather. That the peak here is actually 550. Write that neatly. The peak here is going to be 550. That's the peak. Okay. Anyway, don't worry much about it. All you need to know is that you will see a normal distribution here. Now, why is that? Why does it? What exactly is the moral of the story? The moral of the story is the sum of random variables that you see here. The sum of random variables. They're basically a bunch of a sum of entities that are random. They are called the random variables. Sum of random variables. This is slightly, it is a term that you wouldn't have really heard of well unless you have done a course in statistics. But just see random variables as simply random entities which can take any values. Right? Now, whenever the resultant, this is the resultant. Whenever the resultant is a sum of several random variables, whenever the resultant is a sum of a few random variables, a few random entities, random variables, then you will see a normal distribution like this. You will see this distribution whenever the resultant is a sum of few random variables. This goes by the name. This is actually a very well-known theorem in statistics, rather probability. It's called the central limit theorem. So I have said it in a really easiest possible way. Don't worry much about the word theorem here. It's sort of scary for many of you people who don't like math much. But all I'm saying here is that the sum of random variables, right? This sum of random variables is this resultant, and that resultant is generally a bell curve if it's sum of few random variables. And that is how this emerges. This always emerges when the resultant is a sum of random variables. This is in fact true in nature. Whenever you see an experiment, the sum total will basically, the resultant that you are plotting will basically be a bunch of random events put together, right? Okay, so let me go to the new slide, and let me ask the next question. Okay, the next question is actually in the first slide itself. The next question is this: how does this emerge? What is the reason behind the emergence of this thing? We gave some reason for the left plot, this one. So what's the reason for this one? Is what we'll be covering in the next lecture.